Sorry about that. I hate when that happens. I wasn't watching the clock, and this thing cuts me off at 15 minutes. All right. So, yeah, it's not tangent to the circle if it's all we know is it's just an array. Okay, it is possible to draw two circles so that no common tangents can be drawn. Well, this is what they want you to think of. You could try to be really wacky and draw two circles like I tried to do for number 5. If I draw any two circles like that, and they don't even have to look like they're kind of on the same level. Oh, how come that one moved? Great. And I could draw, these kind of wherever I wanted to, and you can imagine that there's some tangent line that goes through here, and I mean, I'm a little bit off, but there's probably some tangent there, and that would kind of have to be tangent somehow to both circles, no matter what I did with, no matter what I did with these two circles. There's always going to be some kind of connector or some kind of line. It's kind of externally tangent, like this. Again, I'm off a bit. That would have to connect the two. Well, that's all fine and good. You're going to have some tangents that would connect like this or like this, until you start to do stuff like that. Now I cannot imagine any line that's going to be tangent to both circles. If you kind of think of the class of all the lines that are tangent to this and the class of all the lines that are tangent to that, actually I can show you that in Sketchpad just a second. Here I'm showing you all the lines that could ever possibly be tangent to that outer circle, and notice none of them ever are going to intersect the inner circle. You can kind of do the same thing with all the lines that are tangent to that inner circle, but for that one they're going to intersect the larger circle, but they'd always be secant. They wouldn't be tangent. Okay, well that was fun. Okay, so there we go. It is not always possible. So sorry. Yes, this is also false. All right, angle inscribed in a semicircle must be a right angle. All right, semicircle means this has to be a diameter, and we're just talking about half that circle, and the point has to be something on on the circle. That means that's what needs to be inscribed. If it's inscribed in a semicircle, then yes, this would be the center of the circle. This angle would intercept an arc that's 180. I think this is the other most forgotten thing. I said it was about tangents. No, it's about this. Angle inscribed in a semicircle must be a right angle. So that is true. There's no way around that. That's one of the theorems. Okay. When one chord is farther from the center of a circle than another chord. Okay, so I need a circle. I need two chords that are different distances away from the center. So there's one. Here's one that's sort of closer. And that's trying to be wacky, but it can't really be that wacky. Okay, if that's the center of the circle, there's the distance from that chord to the center. If that's perpendicular, and here's this chord's distance from it to the center. Okay, so yeah, distance to the center is defined by this little thing. So if one chord is farther from the circle than another chord, so this is what they would call if one chord, and this is the one that this chord is the other chord. This is the one that's, oh, I'm sorry. This is the one that's farther away. I'm sorry about that. That didn't make sense. If one is farther away than the other, so this is one, this is the other. I thought it was being so cool. Alright, if this one is farther away than this one, like this definitely looks greater than this. And the chord farther away is longer than this one. Well, the longer of the two, no. This you can definitely tell this appears, even in my little example, and I think it would in any example where this was really farther than this. This is actually shorter. The one that's farther away, I mean, if you think about cramming a chord into your circle and pushing it farther and farther out away from the center, it's going to have to start to get shorter as you get farther and farther away. These ones really close to diameters are the longest ones, and then they'll get shorter and shorter as you go farther out. So this is, they just wrote this backwards in order for it to be true. If they would have said shorter, that would have been true. So let's change that to the purple truth here to give you something to think about. All right, shorter makes that true. Okay. All right, so that completes the, whoops, wrong color. That completes the true-false list here, and there they are. There's only 3 trues actually in there. Okay, number 9. In circle O, remember all that implies again, that we're talking about the center of the circle there. If the measure from arc A to B is 100, well, you know what? If this is already perpendicular and bisect D and all that stuff, I'm just going to go ahead and write this in to make my life simpler. A to D is 100, D to B, or sorry, A to D is 50, D to B is 50 if that whole thing's 100. Then the measure of arc A to C. Okay, that's what we're looking for. How far is, or what's the degree measure of that arc? Well, if this is a diameter, and it is because they tell us it goes through O, then from C to D would be 180. So what's left here from C to A is just 180 minus, ooh, lightning alarm. I don't know if you can hear that from here. All right, 130 degrees. All right, if the radius of O is 17, I don't think I have to erase this stuff. If the radius of O is 17, so this is 17 from O to C, and A to B is 30, well, you know how I like to write that. I'm going to write that as 15 to 15 because I already know that that's a bisector and I don't want to mark these overlaps. Then what's the distance from O to E? Okay, time to draw this a little expanded here. I have O, I have E. I know that's a right angle. I have B. I know the distance from E to B is 15. I know the radius of the circle, there's one right here, is 17. That's what I think people are going to miss, that there's a radius right there, and that's perfectly nice to use that as the radius of the circle. Yeah, OC is a radius, but there's a bunch of them. Anything from O out is 17, and I think that's going to be hard for people to see, and I'm looking for OE. And we have our old friend, the Pythagorean theorem. Okay. And guess what? Yet again, they give us one that turns out to be a nice Pythagorean triple. Life isn't always this pretty. It has happened 3 times so far in this chapter review. They're starting to run out of triples, actually. They haven't used 3, 4, 5 yet. Oh, actually, no, they did. They did the 6, 8, 10. Anyway, so that's Pythagorean theorem again. I just thought of something here. I didn't actually erase the measurements from number 9 when I went on to number 10, and maybe I should have. I'm thinking of, I'm trying to think of the craziest questions you might see on the test, and there could be questions where they combine things like this, like you know some stuff about these angles and these arcs in here, and then you got to try to find out stuff like this, like we did on our first quiz. And you might want to try to find this angle based on this arc and that kind of stuff, and you want to use trig to figure out one of these. Right now, if I use trig on this and try to figure out the measure of this arc, I bet it's not 50. So I should have been more careful about that, and I should make tests so that you could go about solving this either way, whether you use trig or not. We try to be careful about that. So just as a side note there. All right, moving on. If AB is congruent to BC, now these are segments, so I can just go ahead and mark those the old way we're used to. If AB is congruent to BC, and the measure of arc B to C is 80, well, you know what I want to do before I keep reading the question? I want to say the arc from A to B is 80, but it's kind of small to write that in there. But that would, of course, be the same arc as that. Then the measure of angle A to B to C, I'm looking like this. Well, you know what? I'm going to go ahead and do it. That's 80 in there, in that arc. A to B to C, I could figure that out. That's like the alligator eating this arc out here, this big arc from A to C. I know this angle I'm looking for is half of this arc out here. Well, this arc out here is the rest of the circle that I don't know yet. This has to be 200 degrees because 360 minus the 80s I know about is going to be 200. 360 minus 160, 200. So if this is 200, then that little guy in there has to be 100. Okay, and I bet I have to get rid of all that again to go on to number 12. All right, in number 12, you can pause right now and look at that for a minute if you need to. In number 12, this was from 11. Yeah, the next step was the 200 divided by 2. In number 12, it tells me that the measure of angle D is 110. That's right here. Oh gosh, this is too small. I wonder if I could make this bigger. If that's 110, then what's B to C to A? This angle here. Well, I want to say that this is a lot harder actually. I can figure out what these two arcs are because I know that this is one of those external angle things here. Let me show you about number 12 here. In general, on number 12, if I have a tangent and a tangent, I know that this angle out here is half of the difference of the big arc minus the little arc. I don't know what these arcs are right now, but I can find them out because I know that they have to add to 360 because together they make the whole circle. Whoa, what happened to my page? That was crazy. All right, it's back. I can call this one x because that's the one I care about more, and I'll call this one the rest of the circle, 360 minus x. We've used that trick before. And I know that 360 minus x, so, you know, one arc minus the other one divided by 2 is 110. They tell me this is 110. And I can figure out what x is. This is 360 minus 2x, and that equals 220. Running out of space already. I had to multiply both sides by 2 at the same time, and then I get the fact that 360 minus 220 is 2x, 360 minus 220 is 140, so x must be 70. And if x is 70, that's kind of nice because, look back at our circle, if this little arc in here is 70, then I know what this is. This arc intercepts that arc on the, it's an intercepted inscribed angle kind of thing. And that's the situation where it's exactly half. Wow, that was a lot harder than I thought. Okay, be on the lookout for those. And it's sort of innocently here between something that's kind of easy and something we're not going to even do, remember, because that's a proof. Okay, we could talk about what that's about, though, because I'm sure the concepts are something you might have to think about. If arc BC, okay, let me get rid of the stuff here. If arc BC is congruent to arc AB, or they have the same measure, well, then I would know things like this. That's the one that no one ever gets surprised by. Why would AC have to be parallel to DB? Well, we could figure this out. I know that since I have the isosceles triangle here, I could use itbat. I could get that congruent to that. Remember, there's that tangent theorem that says this point D, if it's tangent to both, it's got two tangents to a circle. Those have to be congruent there too. So I have a second kind of itbat here. I have that angle is congruent to this angle. Oh wait, I saw something completely easier. Let's draw a radius. Center of circle. I don't know where it is. It's probably not on AC. Radius. Guess what? Radius would have to bisect. If these are the same, the arcs are the same, and everybody's isosceles and happy and symmetrical, this is going to have to be a perpendicular bisector of this segment. Great. And if that's, so it's perpendicular to this one, but guess what? This is also tangent at B here. This BD segment is also perpendicular here to the radius. So now I've got AC and BD both perpendicular to the same line here. Therefore, they must be parallel to each other. That's an old one. Blast from the past that we didn't use that much. Okay, but again, there's no proofs on this test, but that kind of thing might be something you could pull out if you're trying to do these calculation questions where you've got to find angles and stuff. Realize that if there's a tangent and you have these congruent arcs like this, these are going to be parallel. We've done other situations like that where there's been where there's been parallels on parallel chords and things like that, and that does stuff like cut off congruent arcs and all kinds of nice, easy, predictable stuff like that. Okay. All right, moving on to number 14. If the measure of arc AC is 40 and the measure of, gosh, I wish I should make this bigger. If arc AC is 40 and arc BD is 28, oh, this is just how we need it then for our regular old, how come my pen didn't go fast enough on that? The regular old bow tie questions, this thing kind of looks like a plus. It's the average of this arc and this arc to find this angle. Then what is AEC? It's purpose-built for this problem. They handed it to us that we're talking about 40 plus 28 divided by 2. And that would be 68 divided by 2, which is 34. So that is, yes, supposed to be that easy. 15, if AE is 10, oh, wait, I can tell right now. This is one of those problems we're not doing. This is about the segment lengths in a chord situation. It's actually very cool. I wish we were doing it, but we're not. All right, number 16. If the measure of arc RS is 120, this is a 120-degree arc right here, and the measure of arc ST, which is this thing out here, is 160, what's the measure of angle P? Well, in that situation, I don't know why that keeps doing that. Maybe I should just do this every time. Maybe I have to be this nice about everything. Okay, in that situation, I normally know that, and that's a tangent, that this angle out here is half of the difference because it's on the outside. Take that one minus this one and divide by 2. I'm going to get this angle over here. But the problem is I don't know what the one is in here. But since this is 120, I know the rest of the circle other than this. All this stuff has to add up to 360. So 360 minus the stuff I know is the thing I'm looking for. And that tells me what it is. And then it would have to be, well, if this is 160, this is 200, it'd have to be 80. You could do that with a calculator if you need to, but then this would be 80. So then for 16, what I need to be finding then is 160 minus 80 divided by 2. And that's 80 divided by 2, which is 40. Okay? Not bad. Not quite as easy as that last one, but only one little step more. And again, number 17, this is one of those lengthy ones. Length of PT, length of PS, length of PR. I'm a little bit sad, but no, we're not doing that.